Hello everyone, welcome to this lecture series in linear algebra. Today we are going to talk about coordinate system and the change of bases. Uh, about coordinate system, as you know that for a two-dimensional system we used to have xy plane where x-axis is taken as a horizontal axis and y-axis we take as a vertical axis. Okay, so the xy plane is a x-axis and y-axis, they act as the elements for the two-dimensional space R2. Okay, so if you know that if we know the unit vector along x-axis, we represent it as 1 comma 0, and along y-axis 0 comma 1. So if I take these two vectors, a column vector of two elements 1 0 and a column element of vector of two elements 0 1, then they form a basis. Okay, 1 0 0 1, these two vectors form a basis for R2. Okay, so we use this in our say graph paper also. Okay, the horizontal lines and vertical lines, okay, to draw sketch in two dimension. Okay, so these are coordinate system, but is it unique? Can we use other than x-axis and y-axis to make a two-dimensional system, coordinate system? So yes, we can use any basis. Okay, so that's what we are going to discuss today, and then how we can change from one basis to another basis. Okay, so similarly in R3 you know that we take x-axis, y-axis and z-axis in standard basis. Okay, also can we take another basis for xyz space? Okay, so let us talk about this. So first we'll talk about unique representation theorem, then what is b coordinate of x and how we can change the basis from one basis set to another basis set. So first the unique representation theorem. Okay, so let you have a basis b uh, for a vector space V. Okay, and then for each vector x in V there exists a unique set of scalars c1 c2 so on cn such that x can be written as a linear combination of b1 b2 bn with these weights c1 c2 and cn. So we know that these b1 b2 bn, these vectors are bases for V, then that immediately means that you take any vector in the vector space, that vector can be written as a linear combination of basis element. Okay, so we can write x as a linear combination of b1 b2 bn for scalars c1 c2 cn, but this unique representation theorem says that this set of scalars c1 c2 cn has to be a unique set. Okay, so we are going to prove that this set of scalars is unique set. Okay, so let uh, us can start with that. Since b spans V, because this is a basis for V, so the vectors in this they span the vector space, so definitely there exists scalar c1 c2 cn such that any vector x in V can be written as a linear combination with these scalars. Okay, now if this is not unique, okay, that means there is another set of scalars for which we can write x as a linear combination, then we will prove that that set and this set must be same. Okay, so let there be another representation for x, that x can also be written as a d1 b1 plus d2 b2 plus so on plus dn bn. That means we can write x as a linear combination of bases by using another set of scalars d1 d2 dn. Okay, so we'll just prove that these two set of scalars are just same. Okay, c1 must be d1, c2 must be d2 and cn must be dn. To prove this we just subtract these two equations. Okay, and so left hand side becomes 0 and right hand side we can combine b1 terms, b2 terms and so on bn. So we can write it as c1 minus d1 b1 plus c2 minus d2 b2 plus so on cn minus dn times bn. Now you can see that it's a homogeneous system of equations. Okay, so this c1 minus d1 is a coefficient of b1, c2 minus d2 is a coefficient of b2, so on cn minus dn is coefficient of vector bn. So it's a system of equations and right hand side is 0, so it's a homogeneous system of equations. And b1 b2 bn, they form a basis for V. Okay, and we know that the vectors in bases are linearly independent. So if you remember the result that if they are linear independent vectors will satisfy homogeneous system only with a trivial solution. That means the coefficients must be 0 to satisfy this equation. Okay, so the proof now is simple. Since B is a basis, these vectors b1, b2, bn, they are linearly independent. So the matrix equation, this homogeneous equation, only has trivial solution. That means this coefficient must be 0, the second coefficient must be 0, and last coefficient so on. Okay, every coefficient must be 0. So c1 minus d1 is 0, c2 minus d2 is 0, cn minus dn is 0. So in short, we can say that ci equals di, okay, for every I1 to n. Okay, so c1 equals d1, c2 equals d2, and so on. Okay, so that means the representation is just same, or we have a unique representation. Okay, so if you have a basis for a vector space, then any vector in that vector space can be written as a linear combination of the basis with by using a unique set of scalars. Okay, now the second definition is the coordinate of x related to the basis b, or we in short we call it the b coordinate of x. So suppose B is a basis for the vector space V, and X is any vector in V. Okay, so we know that now we can write X as a linear combination of B1, B2, Bn. So the coordinate of X relative to this basis B, or we also call it the B coordinate of X, are the weights C1, C2, Cn, the unique set of scalars that we said in previous slide. These weights are called the b coordinates of x, such that we can write x as a linear combination of b1, b2, bn, and we write b coordinate of x as this symbol, which is xb, or we can call b coordinate of x. Okay, so x in square bracket and in the subscript the basis symbol b. Okay, so we call it b coordinate of x, and it contains the weights c1, c2, cn. So if we write this, that means the vector x can be written as linear combination of basis vector b using these weights c1, c2, cn. Okay, so the x vector will be equal to c1 times b1 plus c2 times b2 plus so on cn times bn. Okay, that exactly this equation is true. Now, if I denote the uh, a matrix of basis vector, okay, if these b1, b2, bn are written inside a matrix, okay, and we denote it by matrix pb, matrix of bases, then this equation, okay, the vector equation x is equal to c1 b1 plus c2 b2 plus on cn bn is equivalent to this. Okay, so this equation can be written in short as this. Okay, so pb is like a row vector times the matrix of or column vector, so we immediately get this equation. Okay, so this x as a linear combination of b1 to bn can be written in short as x is equal to pb times xb, where pb is the matrix of the basis vector and xb is b coordinate x, that means the scalars or weights c1, c2, cn used to write this linear combination. Okay, we call this matrix pb as change of coordinate matrix from b to the standard basis in Rn. Okay, so this pb matrix is called as the change of coordinate matrix from B to the standard basis in Rn. Okay, so it has say n columns exactly, so it is in Rn. Now, if the columns of PB form a basis for Rn, okay, if PB matrix columns they form a basis for Rn, that means there are exactly n columns. Okay, because we need n independent columns to span this, and each column has n elements. Okay, because they span, they become basis for Rn, so that means these vector also belongs to Rn, so each b1 b2 have n elements. Okay, so that means it will be n cross n matrix, square matrix. Okay, so then it will be invertible. Okay, this square matrix will be invertible because columns are independent, so every column has a pivot position. Okay, so it becomes a invertible matrix, and so we can write this equation as pb inverse x is equal to xb, or b coordinate of x can be calculated as pb inverse x. So we have a transformation here or mapping which is written as x to b coordinate x, and we call this mapping as the coordinate mapping determined by the basis b. Okay, so this mapping tells us how the vectors x are transformed to the b coordinate x, which means the scalars. Okay. Now one example here, say consider a basis B of two vectors b1 b2 for R2. Okay, so b1 belongs to R2, b2 belongs to R2, so that means b1 has two elements, b2 has two elements, and so where b1 is given as a vector in R2 1 0 and b2 is given a vector in R2 as 1 2. Okay, suppose x is any vector in R2 has coordinate vector b coordinate x is given as -2 3, so find x. Okay, so basically if you are given R2 space, okay, and we are given a basis, okay, which, so this basis spans whole of R2, okay, because this is a basis, so their span is whole of R2. Now if you are given any point x in this R2 space such that its location we have to find, and we are given the b coordinate x, that means if we write x as a linear combination of b1 b2, then the weights are given, okay, -2 and 3. So what will be the x, what will be the location of x? So clearly if I write x as c1 b1 plus c2 b2, this is c1 c2, so that means x will be -2 distance in the direction of b1 plus 3 distance in the direction of b2. So we can calculate x easily, or we can use the equation x as pb times xb. Okay, pb is the matrix of bases b1 b2, that is same. Okay, so the b coordinate of x tells us how to build x from the vectors in b, that is we can calculate x as pb xb. Okay, so pb is the matrix of the basis vectors, so basis vector is 1 0 and 1 2, and the corresponding b coordinate x matrix means the weights are given -2 3. So we can multiply these two matrices to find the x vector. So location of x vector is 1 6 in R2 space. Okay, so clearly you can see that what we are doing is the first vector with the scalar c1 which is -2, and second vector with 3 to get this. That means we on the R2 plane we move -2 distance 1 0 along 1 0 vector, and then we move 3 distance along 1 2 vector to reach this point 1 6. Okay, we'll just talk about this again. Okay, so also note that the entries in the vector x is equal to 1 6 are the coordinates of x relative to the standard basis e1 e2. Okay, you know standard basis means that e1 is 1 0, e2 is 0 1. Okay, that means the columns of the corresponding identity matrix. For R2 space, I2 means 1 0 0 1 are the columns. So what we mean here that if you are given this x vector, then we can easily write it as 1 times 1 0 plus 6 times 0 1. So we can easily write it as scalar times the standard vectors, or vectors of the standard basis. Okay, so 1 e1 plus 6 e2. And we know that if we write any vector x as a linear combination of vectors in the bases e1 e2, then these two coefficients they become the b coordinate x. Here in basis is e, so e coordinate x. Okay, so if e is the basis e1 e2, then e coordinate x is same as x. Clearly x is 1 6 and e coordinate x are the coefficients or weights, which is again 1 and 6. So that means that if we are dealing with the standard basis, so the b coordinate or e coordinate x is same as x itself. Okay, so this is also true because in this case the lines are horizontal in R2 and vertical. Okay, so the location of point 1 comma 6 is nothing but 1 distance horizontally and then 6 distance vertically. So x and xb are just same in this case. Okay, but if you are given any other basis which makes the coordinate system of R2, then how much we move in the direction of b1 and how much we have to move in the direction of b2 to reach the x vector will given by b coordinate x. So let us see this graphically, that what we mean by saying this. Say you have a standard basis e1 e2 for R2 space. okay, where E1 is 1 0 and E2 is 0 1, and X we said is a vector 1 6. So if you draw the R2 space using these two unit vectors, okay, so you have X axis as 1 0 and Y axis as 0 1, okay, E2 is in this direction. So this is your R2 space or plane, okay, and if X is 1 6, okay, so that simply means that it is one distance in the direction of X axis, or one distance in the direction of E1, and then 6 distance in the direction of E2, okay, so then 6 distance upward, okay, so we have to move one distance E1 and 6 distance E2 to reach this point X. So that's how the standard graph works, okay. But now if we say that the graph is not with respect to standard basis, but it is with respect to a basis B, which is B1 B2, and B1 is given by 1 0 and B2 is given by 1 2, okay. So here we also noted this, that 1 0 is same as E1, okay, but B2 is 1 2, okay, so B2 is here, okay. So instead of horizontal and vertical line, if we take horizontal line and along the B2, okay, so along this direction we draw the graph, okay, so that these two becomes the standard basis, so they also generate the same xy, sorry, R2 space, R2 plane. So what will happen to this vector x, how we can locate it using this b1 b2? So this b coordinate of x tells us that how we can locate any point x in the R2 space, okay. With respect to standard basis, it is simple that whatever are the values in x, the same distance here they have to travel along the bases, okay. So one distance along E1 and 6 distance along E2. Now if basis is not standard, then b coordinate x tells us that how much we have to travel along b1 b2 to reach this point x, okay. So it clearly tells us that if we travel -2 distance along b1 and 3 distance along b2, then we will reach this point x in the plane R2 space, okay. So if your graph is this, that you have b1 vector which is horizontal and b2 vector which is slanting, and the graph is formed, the R2 space is formed by this graph, then to reach the point x, which is 1 6, we have to travel -2 distance along b1, okay. So b1 is this, so -2 distance mean here, and then we have to move 3 distance along b2, okay. So b2 is upward, okay, so -2 distance and then 3 distance upward, so we reach here 1 6, okay. So this is the graphical interpretation of this b coordinate of x, okay. So b coordinate of x are the weights, okay, such that we can write x as a linear combination of the basis vectors using these weights, okay. So it also tells us that how much we have to move along the basis to reach the location of the point, okay. Now we take one theorem here, that let B be a basis for the vector space V, then the coordinate mapping x to b coordinate x is 1 to 1 linear transformation from vector space V on to Rn, okay. So we already said that this linear transformation from V to Rn, but now we are going to prove that it is a linear transformation. Second, it is a one-to-one transformation, and also it is a on-to transformation, okay. So this coordinate mapping is a linear transformation, one-to-one as well as on-to, okay. So first we'll prove that it is a linear transformation, okay. So let us take two vectors here in vector space V, and because this is a basis, so we can write those vectors in terms as a linear combination of the basis, okay. So let u and v be vectors in this space, so clearly u can be written as a linear combination of bases with respect to some weights C1 C2 Cn, and by unique representation theorem these weights are unique, okay. And similarly v can be written as a linear combination of b1 b2 bn with some weights, say d1 d2 dn. So clearly that we know that what will be the uh, b coordinate of u, okay. If we can write u as a linear combination of bases b1 b2 bn, then the b coordinate of u is the weights column vector c1 c2 cn, and similarly the b coordinate of v is the column vector of d1, d2, dn. Okay, now if we calculate the sum of these two, u plus v, then if we add these two, then you can easily write it as c1 plus d1 times b1 and so on, c plus cn plus dn times bn. Okay, so we can add the corresponding vectors. And so what is the b coordinates of u plus v? Okay, if we write u plus v as a linear combination of bases, then b coordinate of u plus v are the weights, which are c1 plus d1, c2 plus d2, so on, cn plus dn in a column vector. So we can easily write that the b coordinate of u plus v from this equation, b coordinate of u plus v are the weights here. Okay, so it's a column vector of c1 plus d1, c2 plus d2 and cn plus dn. And so it is a matrix. We can decompose it into sum of two column vectors as c1 c2 cn and d1 d2 dn. Clearly you can add, so you will get this column vector. And because this first column vector c1 c2 cn, they are weights in u. Okay, so they are b coordinate of u, and d1 d2 dn, they are weights here, so it's a b coordinate of v. Okay, so that means the uh, sum is preserved. Okay, the that's what we require for linear transformation, that the sum has to be preserved and scalar multiplication has to be preserved. So sum is preserved. Okay, so the coordinate mapping preserves addition. Okay, the second, we have to prove that the coordinate mapping preserves the scalar multiplication. So if we calculate a scalar times u vector, okay, if u is this and we calculate say r times u, then r will be multiplied on this side, and by linearity we can separate it. Okay, so if r is any scalar, then r times u is r times this, and so this is scalar, we can multiply it inside, so each vector will be multiplied. So we get r c1 times b1 plus r c2 times b2 plus so on. And so if we write the b coordinate of ru, okay, because ru is written as a linear combination of bases, so b coordinate of ru we can write as the weights in a column vector. So b coordinate of ru will be rc1 rc2 rcn in a column vector. And because it's a matrix equation, so we can take r outside scalar because it is present everywhere. And because c1 c2 cn is a b coordinate of u, so clearly this equation suggests that the scalar multiplication is preserved. Okay, and so the mapping is a linear transformation because the two conditions are satisfied. Okay, now the second thing that we want to prove is that the mapping is 1 to 1. Okay, so when do we have a mapping to be 1 to 1? We mean that if I have two vectors in the domain, they cannot go to the same vector in the codomain. Okay, so if two vectors in the domain are going to same vector in the codomain, then the domain vectors must be same. Okay, so if I start with the codomain and if I say that there are if two vectors in the codomain, if I put them equal, okay, then their corresponding domain vectors must be same. Okay, so that's how we are going to prove 1 to 1. So let b coordinate of u equals b coordinate of v. Okay, so in the codomain these two vectors are equal, then we are going to prove that their pre-images are also same. Okay, so b coordinate of u, okay, because u is written as linear combination of bases, so with the weight c1 c2 cn, and v coordinate of v, so the weights d1 d2 dn. So these two will be equal, and these two are equal, so that means c1 equals d1, c2 equals d2, cn equals dn. Okay, so corresponding elements are equal, and so that means that the u must be equal to v. Okay, so that means the pre-images are just the same. Okay, so two distinct vectors in domain cannot map to the same vector in codomain. Okay, if it is there, then the domain vector must be equal. So we have a 1 to 1 transformation. For onto, what we need to prove is that for every vector in the codomain there is a pre-image. Okay, so let us take that there is a vector y in the codomain, okay, which is Rn space, and because y belongs to Rn, so y must have n elements, so y can be written as a column vector y1 y2 yn. Okay, so n elements, that's why it belongs to Rn. Now if I take a linear combination of these weights with the bases, that if I calculate y1 b1 plus y2 b2 plus so on plus yn bn, so because it's a sum of vectors, so they will add up to give me a column vector. Say it gives me a vector w. Okay, so because now w is a linear combination of b1 b2 bn, and b1 b2 bn is a basis for vector space v, so this vector must belongs to vector space v. Okay, and also the w vector, because now it is written as a linear combination of v1 v2 bn, so the b coordinate of w are the weights which are y1 y2 yn, so I can write the b coordinate of w as weights y1 y2 yn from here, and y1 y2 yn is a column vector which we already said is equal to y vector. Okay, so what we have proved is for every vector y in codomain there is a vector w in domain such that this holds, this is a mapping. Okay, so for every vector in the codomain there exists a vector w in the domain, so mapping is on to. Okay, so this is our proof for the theorem. Okay, now take one more example here. Say let v1 is a vector in R3, v2 is a vector in R3, and x is a vector in R3, and b is a basis which consists of two vectors v1 and v2. Then b is a basis for h, where h is the span of v1 v2. Okay, so h is a subspace of R3 whose basis is b. Determine if x is in H. Okay, so we have to find whether this x belongs to this subspace, and if it is there, find the coordinate of x relative to b. Okay, so we have to find b coordinate of x. Okay, so first we have to find x is in H or not. Okay, so if x is in H, so that means x can be written as a linear combination of v1 v2. Okay, so whether the system c1 v1 plus c2 v2 equals to x is consistent or not, and if it is consistent, then what are the c1 c2, because those c1 c2 are going to be the b coordinate of x. Okay, so if x is in H, then the following vector equation must be consistent. Okay, c1 v1 plus c2 v2 must be equal to x. Okay, and then the c1 c2, these weights when written in column vector, they becomes the b coordinate of x, so both things will be uh, simultaneously calculated. Okay, so okay, the scalar c1 c2, if they exist, they form the b coordinate of x. So how we solve the system of equation? We know we write the augmented matrix and reduce it to find a solution. Okay, so the augmented matrix here is the left hand side vectors. Okay, and the last column is the right hand side vector. Okay, so first v1 vector, v2 vector, and the right hand side x vector. Now we have to reduce it to equivalent form and then to reduced equivalent form. So in the first row, first element becomes our leading element. We will use this to make the bottom 2 0. Okay, so apply row 2 minus 2 times row 1 impact on row 2, and row 3 minus how much, 2 by 3 row 1 impact on row 3. Okay, so we apply this. Row 1 do not change, and these two elements become 0, and corresponding these element changes. Okay, so now we have done this for many lectures. Okay, again in the second row this becomes the leading element, so we can make this element 0. Okay, so row 3 minus 5 by 6 row 2 impact on row 3, so this element will become 0 here. Okay, so when this becomes 0, you see that this last element also becomes 0, and so it is a equivalent form. Okay, and system is consistent. Okay, because we got two pivot positions and right hand side is not a pivot column, so clearly system is consistent. Now to find the solution, we have to reduce it to further into reduced equivalent form. So we have to make the pivot positions as 1 1, and we have to make this element 0, because pivot position will be the only known 0 element in the column. Okay, so first we can divide second row with 2, then make this 0 later, and then make this 1. Okay, so row 1 plus half row 2 to make this element 0. Okay, now we can divide second row by 2 and first row by 3 to write the reduced equivalent form. Okay, once we have the reduced equivalent form, we can see that this is the column for c1, so this c1 equals 2, and this is the column for c2, so c2 equals 3. Okay, So clearly system is consistent, so x is in the H, and b coordinate of x are c1 c2, and c1 is 2, c2 is 3, so we have the solution. Okay, now the second thing that we are going to do is the change of bases. Okay, so if we are given two sets of bases for the same space, then how we can move from one set of bases to another set of bases. Okay, so when a basis B is chosen for a vector space V, the associate coordinate mapping is onto Rn and provides a coordinate system for it. So we just prove a theorem that the mapping is onto, and each x in the V is identified uniquely by the B coordinate vector xb. Okay, so we have said that if this is true, then for every vector x in V, we can write x as a linear combination of bases, and the weights are known as the B coordinate x, which are unique. Okay, by unique representation theorem. So in some applications, a problem is described initially by a basis B, say, but the problem solution is aided by changing the basis to a new basis C. Okay, and each vector assigned a new C coordinate vector. Okay, so just like x is related to basis B, then x will also be related to C. So just like we have B coordinate x, we will also have C coordinate of x. Okay, so now the question is how we can move from B basis to C basis, or if B and C bases are given, then how we can find the C coordinate of x if you know the B coordinate of x, and so on. Okay, so how the C coordinate x and B coordinate x are related for every vector x in the vector space. Okay, so let us say visualize this using two graphs here. Say there is a basis B1 B2. Okay, and there is a vector x in this space, and this vector x is see 3 times b1 plus b2. Okay, so x is written as 3b1 plus b2, and similarly there is a basis c1 c2, and the same vector x is written as 6c1, and then moving this 4 times this side, so 6c1 plus 4c2. Okay, so if there is a x vector in the vector space V, which can be written as 3b1 plus b2, so it can be written in terms of basis of B, and also it is written as 6c1 plus 4c2, okay, in terms of basis of C. Then clearly we know that this says that the B coordinate of x is a column vector 3 1, and C coordinate of x is a column vector 6 4. Okay, so how these two are related, how we can if one is given, how we can calculate second directly if we know the basis, and so on. So these are the questions to be answered here. So now we will learn the connection between these two coordinate vectors. Okay, so this result is true, and we can utilize this, that if say B is a basis for the vector space V, and say there is another basis C for the vector space V, then there exists a unique n cross n matrix P B to C such that the C coordinate of x is equal to P B to C times the B coordinate of x, where this P B to C is the change of coordinate matrix. Okay, sorry, this P B to C is called the change of coordinate matrix from B to C. Okay, and the columns of P B to C are the C coordinate vectors in the basis of B. Okay, so basically this matrix, which is B to C, okay, is the C coordinate vectors of the basis B. Okay, so this matrix is given by this. Okay, it's a matrix of C coordinate of B1, C coordinate of B2, so on, C coordinate of Bn. Okay, C coordinate of B1 means that if we write B1 in terms as a linear combination of basis C, then what are the weights? Okay, so that means if I write this B1 as a linear combination of these C1, C2, Cn, then what weights are required? Okay, those weights will come here in this column. Okay, similarly if I write B2 as a linear combination of basis C, okay, so if I write B2 as a linear combination of this, then what weights are required? Okay, so basically these columns are weights when the vectors in basis B are written as a linear combination of vectors in basis C. Okay, so this is P B to C, the change of coordinate matrix from B to C. Okay, so if we are changing the coordinate matrix from B to C, so we have to write the that means the vectors in the old basis in terms of a linear combination in the vectors of new basis. Okay, and that will form the PBC matrix. And so and the C coordinate of x and B coordinate of x are related by this equation. Okay, so how to find this PBC? Okay, PBC. Okay, if you are given these two bases. Okay, so let x be any vector in the vector space V. So clearly x can be written as linear combination of basis B, and x can also be written as a linear combination of basis C. Okay, so x can be written as PB times B coordinate x. Okay, so that means x is a linear combination of basis B, where PB is the matrix of B1, B2, Bn, and B coordinate x means the weights needed for this linear combination. Similarly, x is equal to PC XC means PC is the matrix of C1, C2, Cn, and C coordinate x means the weights needed to write x as a linear combination of C1, C2, Cn. Okay, so if now I start from here and calculate xc, now because PC is invertible, xc can be written as PC inverse x. Okay, so C coordinate of x can be written as PC inverse of x, and because x in the from the first equation is PBXB, so we can write it as PC inverse PB times B coordinate x. So clearly this equation clearly suggests that the PB to C matrix is PC inverse PB. Okay, and so we can easily calculate the matrix PB to C by calculating this, and in fact we can row reduce to this using the augmented matrix. Okay, so if we start with the augmented matrix PCPB. Okay, so PC means the vector C1, C2, Cn. Okay, C matrix of basis C, and PB means the matrix of basis B. If we write them as a augmented matrix inside a single matrix and row reduce the PC matrix to identity, then automatically this right hand side PV will convert into PC inverse PV, which is PB to C. Okay, so it is easy to calculate PB to C by using this method by writing augmented matrix and reducing the first half into identity. Okay, so let us say take one example here. Let you have B1 vector, B2 vector both in R2, and C1, C2 are also in R2, and consider basis for R2 given by B, which is two vectors B1, B2, and C is also a basis consisting of vectors C1 and C2. Okay, so this is a basis for R2 because there are two vectors linearly independent, so they will span whole of R2. Similarly, C1, C2 are linearly independent, they will span whole of R2. Okay, so both are bases. Now find the change of coordinate matrix from B to C. Okay, so if we have to find P of BC matrix. Okay, so how we can find that is we can write the augmented matrix of PC and PB and then reduce it. Okay, so matrix of PC will be the matrix of C1, C2, these two vectors, and matrix of PB will be B1, B2 vector in a matrix. Okay, so we can use this augmented matrix PC and PB, where PC is the C1, C2 combined matrix. So 1 minus 4, 3 minus 5. Okay, so this 2 by 2 here is a PC, and B1, B2 they form the PB matrix. So minus 9, 1, minus 5, minus 1. Now if we reduce these first two columns into identity, then the last two column will automatically become the coordinate matrix from B to C. Okay, so we have to make this element 0 using this leading one. Okay, so row 2 plus 4 times row 1. Okay, so impact on row 2, so clearly minus 4 plus 4 0, minus 5 plus 4 times this, so 7, 1, 4 times minus 9. Okay, so minus 35, minus 1, minus 20 is minus 21. Okay, so only second row change, first row remains same. Okay, impact only on second row. Now we have to make this as 1, the diagonal here. Okay, so divide second row by 7. Okay, then we have to make this element 0 to make this 2 by 2 as identity. Okay, so row 1 minus 3 times row 2, impact on row 1. Okay, so we can use this to make, so clearly this 1 0 0 1 it becomes identity, and so this side we immediately got the change of coordinate matrix from B to C. Okay, so PBC, the change of coordinate matrix from B to C is 6 4 minus 5 minus 3. Okay, Okay, let us take another example here. Consider two bases. B is a basis and C is a basis for a vector space V, such that B1 can be written as a linear combination of C1, C2, okay, where C1, C2 are elements in basis C, okay, and B2 can be written as a linear combination of C1, C2. So what is given is that the vectors of the basis B are given in terms of the C, okay. Also x is written in terms of the basis B. Find the C coordinate of x, okay. So what weights are needed to write x as a linear combination of C, okay. So clearly what you are given is the B1C, okay, B1C coordinate of B1 is 4 1 column, C coordinate of B2 is -6 1 column, okay, because C coordinate of B2 means if we write B2 as a linear combination of C1 C2, what are the weights? So weights are -6 1. B coordinate of x is given because x is written as a combination of B1 B2, so 3 1, okay, the weights. And what we have to find is C coordinate of x, okay, so xc we have to find. So we know by formula C coordinate x is P B to C xb, and P B to C is a matrix where B1 C and B2 C, like writing B1 B2 as a linear combination of C1 C2, okay. So they are already known. So this PBC is a matrix of 4 1 minus 6 1, and the XB is a matrix of 3 1. So we can easily calculate the product of these two matrices to find 6 4 are the C coordinate of x. That means if I write x as a linear combination of C1 C2, these are the weights. So x can be written as 6 times C1 plus 4 times C2. Okay. So this is the solution. Okay, so finally I take one last example here. Let you are given again two bases. B is a basis for vector space V and C is a basis for vector space V. And suppose that C1 is written in terms of B1, B2, C2 is written in terms of B1, B2, B3, and C3 is also written in terms of B1, B2, B3. Okay. So now the vectors of C are written in terms of basis B. Okay. Find the change of coordinate matrix from C to B, okay, not from B to C but C to B, okay. So clearly this can be used. And find the B coordinate x for x equal to this. So C coordinate of x is given, okay, C coordinate of x is 3 4 1, and we have to find B coordinate of x. So clearly now we have to find the matrix PCB, okay. So P, instead of PBC we have to find PCB. That means if I write C1 C2 C3 in terms of basis B, what are the weights? So that means if I write C1 in B coordinates of C1, that means C1 as a basis linear combination of B, C2 as linear combination of B, C3 linear combination of B. What are weights? So weights are given here, okay, 4 minus 1 and 0, so that's first column. C2 as linear combination, so minus 1 1 1. C3 as a linear combination, 1 minus 2, 0 1 minus 2, okay, B1 coefficient is 0. So clearly this is the matrix for the change of coordinate from C to B. Now if I have to find XB, then XC is given 3 4 1, so XB is PCB XC, and so we just need to multiply these two vectors to find that the vector B coordinate x is 8 2 2, okay. So that means if I write x as a linear combination of B1 B2 B3, then these weights are required, 8 2 2, okay. So this was about change of bases, okay. So in the next lecture we will talk about eigenvalues and eigenvectors. So this is again a very important topic, okay. So till then, take care and have a very nice day.